Okay, so you occupy one slot. Now, what is the implication of that? It means that if there's collision, it's 100% overlap. It's not partial overlap. Previously, it's not slotted. So you can have partial overlap. Now, because everybody is synchronized, if two people transmit, it's complete 100% overlap. And with that, it means that your collision window is half. Previously, it was 2 TXM. Now your collision window is half. And because your collision window is half, when you do all these maths, everything is improved by double. Okay? So that's what I have. So this is the protocol. Ready to packet? Packet ready to transmit? Yes. Delay to beginning of next slot. Transmit. Wait for your timeout. Did you get your acknowledgement? Yes. Good. That means successful. No. Back off. Wait. Put to sleep. Wake up again and transmit. Okay? Right. So if you do that, everybody obviously have to be synchronized. Okay? You have to ensure that it's synchronized. Okay? And it's called slotted aloha. So as I mentioned, the contention window is reduced to TXM. If you plug in the formula again, the successful one will be e to the minus TTXM times lambda instead of e to the minus 2TXM times lambda. Alright? Do the differentiation, set it to 0, find the maximum lambda will be 1 over TTXM, and the traffic carried out, the maximum traffic carried out is 1 over E instead of 1 over 2E. Okay, and that is the plot that you saw just now. This is the plot. What occurs when you offer traffic, the amount of traffic you offer is 1 erlang. Of course, you can offer more than 1 erlang, but whatever is carried cannot be more than 1, because the pipe is already full. Okay? And the maximum traffic is 1 over E. So you can see it's double. Okay. Any questions after this one? Okay, let's do an example. Right. A pure Aloha system uses 56 kilobits channel, the second channel. So that's the transmission rate. On average, each terminal originates a 1024-bit packet every 30 seconds. So that means you got 1 packet every 30 seconds. So what is lambda? 1 over 30. Arrival rate, 1 over 30. What is the maximum effective number of terminals the system can accommodate? That's part 1. Part 2 is how many terminals can the system accommodate using slotted aloha? Okay, so now you have a 1024-bit system and you're transmitting at 56 kilobits. That means the transmission time is 18.3 milliseconds. To transmit 1024 bits at 56 kilobits per second, it will take you 18.3 milliseconds. All right, so that means the average traffic that each terminal will generate will be the arrival rate, which is 1 over 30, times the transmission time. That's what we call the service time. So that will be 6.1 times 10 to the minus 4 early. So on the average, this is what each terminal will generate, the traffic that each terminal generates. Now we know that the maximum traffic that you can carry is 0.18. Right? We just proved it, maximum traffic, 0.18 erlang. So if there are n terminals, n times 6.1 times 10 to the minus 4 must be equal to 0.18, because it's the maximum you can carry of successful traffic. Okay? So that's what we get. 6.1 n times 10 to the minus 4 equals to 0.184. Therefore, the maximum number of terminals that you can select, that you can support, 300 remote terminals. Okay. Any questions? If you use slotted aloha, then this maximum will be equal to 1 over E, in which case the number will double to 603 terminals that you can transmit. Okay, 603. So that's slotted alone. And that's the basis of how we started to improve the generations of different protocols. Okay, and the first improvement is this guy. Carrier sense multiple access. Okay, what carrier sense multiple access does is this: when you have a packet ready to send, you listen to the channel first. That's called carrier sensing. Okay, you listen to see whether it's idle. If it is not idle, you cannot send. If it's idle, then you can send based on some rule. Okay, see, you listen. I put there A, B, C. These are the rules, which I will elaborate on because we're going to look at 3 different systems. Okay? So, based on those rules, you send, alright, okay, at the beginning of the next slot, because you always send on a slot basis, because we know slots are better. Okay? Then, you wait for a timeout period. This is 2 propagation delay aligned to slot time. Did you get your acknowledgement? If you got, great, you are successful. If not, you back off. You calculate this number. This is called a random back off integer. Based on that number, you sleep according to that number. When you wake up, you try again. Okay? So what's the difference here is this guy, the carrier sensing. In the centralized system, you did not do carrier sensing. You got something to send, you blast it off and hope for the best. So now you're doing carrier sensing. Listen before you send. Because you know it's busy, no point sending. You know you won't be successful, right? And the other guy gets clobbered. And then that gets it, right? So no point. Okay. So now we see variants of this. The first one is called non-persistent. Okay? So it says, if the channel is idle, send a packet. If the channel is busy, station uses a backoff algorithm following the path C to reschedule the transmission. At the time of retransmission, channel is sensed again and the algorithm is repeated. This is not the system. Okay, let me repeat what's happening. I got packet to send. I listen. Is it idle? Idle, I send. I listen. Not idle. Back off. Random number. Sleep. Wake up. Listen. I don't know. Idle. Now I said. That's not the system. Okay? T persistent. Okay? So you transmit with a certain probability P. That's why we got it P. Alright, again, let's see what happens. If channel is sensed idle, a random number uniformly distributed from 0 to 1 is chosen. If selected number is less than or equal to P, the packet is transmitted. If not, station waits tau seconds and repeats the algorithm. So let's see if it's busy. Yeah, idle. If the channel is busy, station persists in sensing the channel until it is found to be idle and then proceeds based on the above. Okay, shall I repeat it? I go back to the same. I listen to the channel. Idle, great, I throw a coin. Come up with a number. Find the number. Is it less than or greater than P? If it's less than P, I send. Okay? If it's greater than P, I wait tau seconds and then I try again. Repeat. Pick my random number. That is if the channel is idle. If the channel I listen is busy, then we continue listening, busy. Free. How's the coin? Okay, be persistent. And try. Okay?
Excuse me. Yeah. Is this tau seconds a random number?
No, it's not. No, it's a different number. Okay. By the way, there's a lots of maths behind all this when they prove all this. Okay. this. When P is 1, right? Then we call it a persistent algorithm, one persistent algorithm. Okay? Right? So P persistent is depending on which value of P. Now, it turns out that too much work on this P persistent. Marginally better, but too much work. So, most of the time we just use the non-persistent, easier to handle. Okay. But even with this, it's still not good enough. Because there's a couple of problems that are not solved by this algorithm. It's still not enough. Okay? So, this is the next enhancement. There are 3 levels of enhancement, and then I will finish today. Okay? Since I'm talking about this. Okay. The first enhancement is called CSMACA, or Carrier Sense Multiple Access with Collision Avoidance. Okay? Alright? So, this is a variation from another method called CSMACD. Okay? Yeah, because I'm not going to do CSMACD. Okay? Collision detection. Collision detection. Alright? We know what is this already. We sense the signal before we send. That's CSMA. CD is collision detection. When we send, I continue listening to the channel. Because I know what I send. So I hear the things which must be my data. But if I hear the channel and it doesn't sound like my data, like corrupted, I immediately stop because I know I've done a collision with somebody else. If I'm the only sender of my signal, I should be able to hear it. But if I hear the channel and it doesn't sound like my signal, there must be a collision. And I immediately stop. And then I back off and I try again. Why is this important? This is Ethernet. Ethernet uses that. But Ethernet is wired. Huh? There's no wireless Ethernet. Huh? Okay? Alright? There's no wireless Ethernet. And we can't do this because in a wireless environment, you can't be sending and listening at the same time. You can't. That's why this one doesn't work. So we have to use a different strategy. So instead of collision detection, we do collision avoidance. And this is what this is. Alright? Of course, we still have X and all that acknowledgement. So how does this work? Okay, a lot of words, I'll try to simplify it. Okay? Basically what happens is this. You got data to send, okay? And you listen to the channel. It's free. But you don't send immediately. Okay? You defer your transmission for a minimum period called the DIFS time. The distributed is a long name. Huh? Distributed Coordination Function Interframe Space, DIF. Only after the DIFS period do you send. Okay? Why? This is to ensure that it's really, really idle before you send. Okay? That's one reason. The second reason is that depending on how long I set this DIFS, alright, this time deferment, I can set different types of time deferments and call them different names. Those services that require urgent attention, I can give it a shorter deferment time because they will await shorter period. So that means you give them priority. By changing the deferment time, you basically introduce priority into the system. Okay? So that's why. Now, after you wait the DIFS, then you send. There are two other mechanisms that we have to take care of. The first one is called the contention window. If there is a collision that occurs, you increase the size of the contention window. Okay, you keep doubling it. The contention window is the window during which everybody has to back off over a range. You know, it's a random number between 0 to CW. And you're increasing CW so that you increase the range so that you disperse, make it more likely that the people will wake up at different times. Okay? Alright? But if the channel is idle and everything is fine, you decrease the contention window counter again. The back-off counter decrements by 1. If the channel idle for each time slot and freezes if the channel is sense busy. Alright, so initially the contention window is set to its minimum value, which is 1. Okay? So I'll show you some examples so that you can see. Now the other deferment time is called the SIFS. This is the short interframe space, SIFS. And you notice the SIFS space is shorter. Okay? Right. That means those messages that are more urgent will use the IFS. You as a normal user, okay, when you want to send a data packet, will always use DIFS. Your recipient, your destination, who wants to send you an acknowledgement, and you're anxious, like you're waiting, where's my acknowledgement? So the destination node knows that you're waiting. The destination node in sending the acknowledgement will use SIFS. Because that means the destination node will have priority to send the acknowledgement compared to another user who wants to send data. Because SIFS is shorter. Alright? Okay? The backoff window is a number that you saw just now increase and decrease. So a user may have a certain backoff because of prior collisions or whatever. Okay? You keep increasing or decreasing. Okay? Alright? So in this particular example, he's showing you that a user has data to send, and he has altogether 1, 2, 3, 4, 5, 6, 7, 8, 9 backup slots here before he actually sends the data. Alright? 9 of them. So if a user doesn't get the acknowledgement, of course you have to try it again after some backup. Okay? Then the next slide shows you the growth of the contention window. In this case, the initial value is set to 31. Maximum value is 1023, and you can see it's doubling. Basically, it's a multiple of 2 minus 1. It's 2 to the 5 minus 1, 2 to the 6 minus 1, 2 to the 7 minus 1. You can see, right? Okay, doubling. Alright, so now I'm going to give you a simple example because all those description is a bit hard to follow. Okay. So in this example, okay, this is my last slide because I know you're all getting tired. I know my voice is going. Okay, I have station 0, station 1, and station 2. What I'm showing here is that station 1 and station 2 want to send data to station 0. Okay, station 1 and station 2 want to send data to station 0. Okay, the channel was busy initially over here, and station 1 had a backoff of 3 slots, as you can see there, and station 2 has a backoff of 2 slots. Alright? So, station 1, the packet arrives. Okay, the packet arrives. What happens now? He has a backup of 3 slots. So he waits the IFS first, then he backs off 1, 2, 3, then he sends his data. Alright, after sending this data, alright, I'm assuming right now that the transmission time is all 0, propagation time is all 0. Okay, but of course in practice it's not 0. Okay, after sending this, station 0 will acknowledge. So after SIFS, he will send the acknowledgement. So FISS is the wrong here, this period is SIFS. He will acknowledge. So now he's finished. Then station 2 wants to transmit. So he waits DIFS, 2 backup slots, and sends. Then station 0 acknowledges. After SIFS, he sends acknowledgement. Okay? Now in practice, you have propagation delay, depending on the distance between the nodes. So if you have propagation delay, then the diagram will change, because it's not the same vertical, it's slanted now. You know what I mean? It's slanted now. So you've got to take into account for that. And there are questions in the tutorials for you to try. Okay? So we slanted something like this. So this is the initial start. So it was busy up to this point. Okay, so this is 0. This is 1. This is 2. Okay, so at this point, he waits for DIFS. This DIFS. Sorry, a little bit small. Then he sends his data. Okay, that means this data will arrive there at that time. Then from here, this is SIFS. He will send his acknowledgement. This is your ACK. Right? Which means he will arrive here. So you can take care of all this propagation. Get the idea? Get the general idea? Okay? So as I said, there are examples in the tutorial. Please try them so that you get a feel for it. Okay, right now I've drawn all these vertical inside this example. All vertical. 0 propagation delay. Any questions? Okay, so for example, station 2 has data that he wants to send here. Okay? What happens is that he's already got data to send. So at this point in time, alright, assuming this also takes the same amount of time to get here. Alright, of course he knows that he cannot send because it's all busy, the channel is busy, right? Okay? So at this point, let's say the time is the same. This time and this time is the same, all the propagation for simplicity. So let's say this time is the same. So he wants to send data, but he has to wait DIFS, right? Which is longer than this guy. Because this is shorter, he already captured the channel. So he has got to wait. So the shortened SIFS time gives priority to the other one that waits DIFS time. Because he wakes up earlier. Okay? Yeah. So that's called collision avoidance. Any other question?
The station is not the same for other channel, other stations.
Same. I'm just taking a simple example here. I think more example more complicated. Alright?
It's the same for other stations.
Yeah. When you send data, you use DIFS. You send acknowledgements, you use SIFS.
Those are fixed.
Fixed. Okay, the questions will tell you how long is DIFS, how long is SIFS. Okay, usually we define it as a function of the propagation delay. Okay, if total propagation delay say is alpha, so I say, okay, DIFS is 5 alpha and SIFS is 2 alpha. Okay, and it takes 20 alpha to send the data packet, 5 alpha to send the acknowledgement packet. Okay, so you have a basis to understand how long or how short are all these times. Any other question?
For the station 2, why the backup time is 2?
Oh, depends on how how lucky or unlucky he has been previously. If he tried and he did not get his acknowledgement, his back-off time will keep increasing. Okay, I'm just taking an example, that's all.
Is there anything to do with the backup counter?
Yeah, this is a back-off counter.
So
Okay,
why not? Why? Yeah.
can it be? If you have not been successful, remember just now we were saying every time you are unsuccessful, your backup counter will increase. You said you didn't get acknowledgement, okay, you increase your backup counter. Alright, but once you're successful, your backup counter go back to 0.
Oh, so the backup counter is, so the backup time is less than 2 to the power of 5 minus 1.
Yeah, so it's, we define it here. Yeah. If a channel is busy, the station generates a random back-off period that is uniformly distributed between 0 to CW, whatever is CW. That's where you get your back-off number. Yep.
Does the sensing of the channel, I don't know, has the population delay?
Does the sensing, yes, of course, there's population delay.
Does that,
Yeah, no, I'm using all these ideas as example. In reality, of course, there will be more.
I mean, is that going to have the backup or sensing?
Sensing is whenever you wake up, you listen.
Yeah, I mean, the listening should have.
Listening can be assumed to be moved. Okay, listening move. Because it's whatever is there. Either there's something there or there's nothing there. Okay? Huh? Any other question? Alright, so this is called CSMA-CA. Alright? Please do try the question so that you get a better understanding of what's going on. Of course, you will do the tutorials later. Okay? So, it doesn't solve all the problems. It doesn't. Okay? These are the two problems it doesn't solve. But I'm not going to find the solution for you today. We're not talking about that. We'll talk about that in the next lesson. Okay? The first problem is called the hidden terminal problem. I will explain the problem to you so you know what it is. Okay? The hidden terminal problem is this. A wants to send to B, C wants to send to B. A and B are in range. B and C are in range. A doesn't know C because they're too far apart. So what happened? He tried to send and he tried to send because he hears nothing. This guy is too far. He hears nothing. So this is a hidden terminal from that guy. Similarly, this is a hidden terminal from this guy. So when hidden terminal occurs, two hidden terminals could be sending to the same guy, collision. That's called the hidden terminal problem. Okay? That's the first one. The next one is called the exposed terminal or exposed node problem. So if you look at the picture, I have node R1, S1, S2, and S3. Node 1, S1 is sending to node R1. Okay? S2 wants to send to R2. But S2 is hidden from R1. R2 is also hidden from R1. But because S1 is sending to this guy, he can hear it because he is near enough to S1. S2 is near. So he hears the transmission also. So, okay, in that case, I better keep quiet. But actually, he wants to send to this guy. His transmission will not interfere with R1 because R1 is so far away. So he's being polite. He holds back. Alright? He holds back. But actually, he can proceed. So that reduces efficiency. So that's called the exposed node problem. Alright? We're going to solve that next week. You learn that history. Interesting? Okay.